All right. So I guess I should begin. Sorry for all the technical delays. And so we'll be actually I will need to toss the second. First, today we'll discuss one problem, and the second one requires a little bit of linear algebra building of that, just not combinatorics. So I don't think it's possible to squeeze it in 1 hour talk. So we'll probably, if you are interested, we'll get into that details in a second talk. And as far as the problems concerned, we are discussing fairness in the context of algorithm design. I'll tell you what this means. We tried to, we came up with a notion of fairness, and using that, we tried to solve two problems, namely vertex cover and feedback vertex set, in the realm of parameterized complexity. So, firstly, what is parameterized complexity? It's a paradigm of algorithm design used for tackling NP completeness. Now, NP complete problems are hard problems, but we just can't let it be because they're hard. They still need to be solved because of applications or other theoretical interests. So how do you tackle them? So parameters complexity. So what do we know about NP completeness? We know that for NP complete problems, in the most general instances, we cannot expect exact deterministic algorithms which run in polynomial time. And I said do not expect because there is a conjecture P versus NP. It is yet to be proven. So, but it is highly believed that P is not NP. So, do not expect. Now, the thing is, what if we relax one of these, some of these conditions? So, let's say instead of exact, I am happy with a non-exact solution. Of course, when I say that comes under the purview of approximation algorithms. So you can have an NP-complete problems where you will get a deterministic algorithm which will run in polynomial time for all instances, but the answer it will return is approximate. Now, of course, this makes sense only if the problem is a optimization problem. For decision problem, it doesn't make sense to have approximation. Yes or no. So, I think. What if we relax the determinism? Then we get something called randomization. So, given a state and value, we go to the next state not deterministically but by random turns. Then, what if we relax the polynomial time requirement? This comes under what is known as exact exponential algorithm. Here, the target is okay. I'm happy with exponential time algorithms, but better than brute force. Let's say there's a problem where the brute force algorithm runs, order to the power 9. I'm happy with exponential, but can I make it say 1.6 to the power 9? It's exponential, but still better than brute force. Or maybe it is the brute force n to the power n. Can we make it to say root n to the power n, something like that? Still better than brute force. And then you have this called general instances. Maybe I don't need to solve it for all each and every instance, but some instance. This is where parameterized complexity comes in. So, informally speaking, what it means is that given a problem instance, there is some other character called a parameter, which I will define what it is. And if the parameter is small, then you get a very efficient algorithm. And you try to design a where the runtime depends a lot on the parameter. So if the parameter is small, you get a very efficient algorithm, and if the parameter is large, you get something better, but you get something worse than what would have been if it was smaller. So it's like it is efficient, deterministic for instances where the parameters are small. This is what the idea is. Okay, so as I said, parameterized complexity. Now, what is a parameterized problem? This formal definition is that given some alphabet, so a language which is a subset of sigma star cross n is called a parameterized problem. And for an instance, This is xk of the language. K is called the parameter. An example would be for since we deal with graph problems mostly, say given a graph, uh, finding a number k, can we find a vertex cover where of the graph G whose cardinality is at most k. A vertex cover is a subset of vertices that if you delete them, the graph has no more edges. Now, what is fixed parameter tractable? This is like the desirable class in parameters complexity. Like in generally, when we do classical complexity, we try to see if a problem belongs to the class P, so polynomial type. Here, since we are dealing with NP-complete problems, this is the most efficient class kind of thing. We try to see if a problem can belong to this class. So it's called fixed parameter tractable. What this whole thing means is that, like, say if you have a graph on n vertices and a problem, a graph problem, and the input is n vertices and the parameter is k. For that problem, say pi will belong to the class fpt if you get a deterministic algorithm which runs in time some polynomial in n multiplied by some computable function of k. So this is called fixed parameter tractable. Now notice here, if the value of fk is small such that means like if k is so small that the value of fk can be bounded by a polynomial in n, then we get a polynomial time algorithms for those instances where the parameter is small enough. This is the idea. Okay. So now we come to if it is NP-complete problem, f should not be a polynomial function because then you will get p equals to.
It is some function.
Some computable function of only k. It does not depend on n, just on k.
K is fixed.
No, k is part of the input.
K is the
Parameter part of the. Okay, now this definition, what we call fair problems. So we have fixed a positive integer t, and we'll this I'll use this notation a lot. This means box t means all the integers from 1 to t, and we call the members of this set as colors. Now a graph is called t colored if there exists a coloring function from the vertex to the power set of t minus, meaning that every vertex has some color from t, say maybe color 2, and notice that the function is from vertex set to the power set of this set minus the empty set, meaning there could be vertices with multiple colors. So you could have something like this vertex A has colors 3 and 4. Okay. Now you're given a t tuple of non-negative integers k1, k2 up to kt, and we say a subset of vertices to be t fair if for every I in t, the vertices of S which contain the color I is ki. So t is something like this, cal t is something like k1, k2, kt, therefore and S is v1, v2, v say 10. So the number of vertices which contain the color 1 from this set is k1. So on for k2. Then we say that S is script t fair. Okay. Now there is some kind of a practical motivation for this. Is like these colors can be used to represent some values of some attributes. So some attributes, like it could be like, let's say you want to form a committee in a, say a town or something, and you need people from various backgrounds and ways. So maybe a color represents someone's income group, someone's age group, someone's gender identity, religion, etc. So vertex cover kind of like covers. So if you pick a vertex of certain color, it kind of covers all the attributes. So that's the fairness being defined over here. Okay, so we'll discuss these two problems in this paper. For today, we'll discuss the first one, vertex cover, and is that you're given a sorry something. So you're given a problem pi. You have what it does is uh, a kernelization algorithm, say script A, it will run in polynomial time, runs in polynomial time. It takes an input, say I'm writing GK because graph, an instance of this problem. It will return an equivalent instance, equivalent in the sense that this is a yes instance if and only if this one is yes, such that the size of this is bounded by some function of k. The size of the graph and the plus this is parameter is this is bounded by some function of k only, computable function. So it doesn't as such solve the problem itself, but what it does, it makes the instance size smaller. Now notice here, once you have a kernel, you have an FPT algorithm because this thing runs in polynomial time. So in polynomial time, you got an instance of size some function of k bounded by some k. Now you run whatever algorithm you knew, maybe the most brute force algorithm. That running time, whatever it is, it will be a function of k. So this is bounded by this is FPT. So this is a technique of designing FPT algorithms known as kernelization, and this is output instance is also known as kernel. So as you say, intuitively speak, kernel is a smaller equivalent instance
I need to go.
Yeah.
Yes. So I guess everything is fine. So any questions?
Sorry, you were saying how the hint.
Oh yeah, the hint is like if you have an FPT algorithm, you have an algorithm that runs in time this much. What you do is you take that algorithm A and run it for n to the power c plus 1 steps, then you can get a kernel. That may not be a very efficient kernel, but some kernel. Now, so we'll try to get a kernel for the fair vertex cover. Okay. First is that if there exists some color for which the number of vertices which contain that color is less than ki, then we just return no. Because we need for every I this to be equal in the vertex cover. Now, if in the whole graph the number of vertices which contain that color is less than ki, then of course you can't get. Okay. No. You have this problem. This problem. T colored graph, integers, parameter is this. So okay. What we then do is now I'm saying no, but what is to keep true to the definition of kernelization, it doesn't solve the problem, it just returns an instance. So what return no means, you can instead of writing then you can say return a trivial no instance, maybe something like this. A graph, say this is a blue vertex, this is a blue vertex, you say I need a vertex cover where there is at least 2 green vertices. This is a trivial no instance. Instead of that, I'm just writing it in one step. But this is for if you want to stay true to the definition, kernelization. Then what we do is, okay, I'll tell you why this is required later on. But what this does is you take kmax of all the maximum of all the ki's. Now for every non-empty subset of box T, you get all those vx's, all those isolated vertices, the degree 0 vertices, whose colors are exactly x. Okay, you take it, put it in Vx. If the cardinality of Vx is greater than Kmax, then keep any Kmax of them and remove the rest from Vx. Finally, we take all possible unions of Vx, we call it I star. So this contains a lot of isolated vertices, I star. The cardinality of this is at most Kmax to the power T, which is at most summation Ki to the power T. This may feel large, but I have said that T is a constant, so 2 to the power T is a constant. Now, if it wasn't, then you had to take the parameter K plus I plus T to get a polynomial, something. Okay. Now, suppose these rules are no more applicable. That means for every vertex, for every color, the number of vertices having this is at least, right? And you have kept away some isolated vertices. Okay. Now, suppose there exists a edge UV. Now, the definition of vertex cover is that for any edge, you need to pick at least one of the vertices in that set. Because you have to kill all the edges. Okay. Now, suppose U has the color I, V has the color J. But the number of vertices I'm allowed to pick for color I is 0, as well as for color J is 0. I have to pick one of these vertices, but I can't pick either of them. So this is a no instance. By definition, I have to pick one, but I'm not allowed to pick. So this is a no instance. Now suppose there exists an isolated vertex which is not in I star. Then what we do is just delete it and return, just delete it from the vertex and return this instance where C prime is the coloring function restricted on this graph. And this tuples, they remain the same. The parameter doesn't change because isolated vertices. Now, why did I do this? Because see, when you don't have color the fairness restrictions, any degree zero vertex can be straight away deleted. Like if you look into the vertex cover colonization algorithm, the normal one, because they don't play any role in edges, so any degrees. But because we have to pick some vertices of some colors, you just can't delete vertex. So I keep a sufficient number of isolated vertices like safely in some other place. Any other isolated vertex, I just delete it. Okay. Now this is like the normal kernel rule for vertex cover. Like if you have a vertex cover of if you want to search a vertex cover of size k, and there exists a vertex whose degree is at least k plus 1, say k is 2, then you better pick this in the solution, because otherwise then you have to pick all its neighbors, and that's not allowed. So similarly here what you have, if there exists a vertex and there exists some color for which in the open neighborhood of that vertex V, the number of vertices which has that color is greater than Ki, then we must pick Vi. Otherwise, you have to pick all its neighbors and you will exceed the color bound for ith color. Yeah.
Because previously there was no instance where you could have gotten. Okay. It's a nested.
No, that I'm assuming. See, this one.
Yeah.
Yeah. I first apply these rules. I see these rules are no more applicable. So now I am. Yeah. Now I am doing the like if else kind of thing.
Correct.
I'm ordering these rules in the order I have mentioned. If else, if else. Okay. Now, if now we are in a situation like the else part, like if else, these rules were there. Here it is. If none of these rules are anymore applicable, like none of these are applicable, then we will return no if the vertex size, the size of the vertex of the graph exceeds some number, or the edge size exceeds some number. How the number comes, I'm telling you, but otherwise we return this instance. Now notice here, if these two conditions are not satisfied, that means what? The size of the vertex is, number of vertices in the graph currently is at most this, and the edges is currently at most this. We know the size of the graph is number of vertices plus edges. Now notice here, the entire thing is bounded by a function of Ki. This 2t may look a bit like odd or something, but I said this is a constant. Otherwise, you have to say function of Ki plus t. But it doesn't. T has been fixed, not a part of the input. So, okay. Now, how to get this number is a bit like okay. Suppose you have a yes instance, then you have a vertex cover. Let's forget about the colors now. Let's say you have a vertex cover of size at most size k. Then why? Because the vertex curve, because this is the vertex cover, F is the vertex cover. Notice, yeah, once you delete the vertex cover, what remains is an independent set. And as there are no more isolated vertices, so each of them must be a neighbor of some element in F. And because of this rule, the degree of any element in F is at most k. So this number is bounded by k times script. And therefore Vg is, this will become k square plus again this k. And H set is at most k squared because you have k elements in the vertex cover. Again, each edge is incident on them, and each vertex can have at most degree k. So edges are at most k squared. To substitute summation ki for k in this condition, you will get this. It's an easy exercise. Okay. So kernelization is done. Anything else? Okay. Okay. Now there is something called tree decomposition. Tree decomposition is where you measure, it's a measure how much tree-like a graph is, because some, like we said, that in parameterized complexity, we try to solve problems, try to come up with algorithms which solve problems for some instances. Now there are problems, NP-complete problems, which are which have polynomial time algorithms when restricted to trees or forests and such. So this notion of tree width is, it's a measure of how tree-like a forest of a graph is. So it's been defined in such a way that forests will have tree width 1, cycles will have tree width 2, and a complete graph on n vertices will have tree width n minus 1. It's like, okay. Now, what is a tree decomposition? It's given a graph, it's a pair called it's a pair of t phi, where t is a tree and phi is a function from the vertex set of the tree to the power set of the vertex set of the graph. So you have a tree and each of these nodes are mapped to some, say this graph, some subset of each of these, they will have some, and it could, that subset could be empty, by the way. Okay. Now some such that some conditions hold. One is that if you take the union of all the images of the vertices of tree, that will cover the whole graph. Okay. Now if there exists some edge in the graph, the UV, there will exist some vertex in the tree, say call it T, such that this is mapped to some subset of the graph, let's call it X, where both E and V are present. For every edge, this should hold. And also that for every vertex, the set of the vertices of the tree which contain, whose images contain that vertex, they must be connected. They form a tree among themselves. So if you have a vertex, say A, and say this node has been mapped to A, some set containing A, you can, and this node is not, you cannot have this node to be mapped to some set containing A, because this has to be connected, all the nodes. Okay. And for any T, okay, now just to make things easier, I will use the word node to mean the vertices of T and vertex to mean the vertices of G. So, okay, and this, for every node, the image of that node is called the bag at, at that node. It's like a bag of vertices, and the width of the tree decomposition is the max of the bag size minus 1, and the tree width of a graph is denoted by them all. Take all possible tree decompositions, take the width and the minimum of that. Okay. Now the thing is, for to design algorithms, we need it's like we need some like using just a tree decomposition. A normal tree may not be easy. So to make our life easier, we have a special kind of tree decomposition known as nice tree decomposition. What it does this, that we have a tree decomposition where the T is rooted at some node. We call it R, such that the bag at R is empty. For every leaf of that, now since we have a root, we can have leaves. So now for every leaf, the bag is empty. And every non-leaf node is one of the following types. One is that it's called introduced vertex node. That, so say this is a node X and this is a node Y. It has exactly one child called Y, and for this has a bag called it phi Y, and for some vertex which is not in this bag at Y, phi of X is equals to V singleton V union, right, for some vertex. So we say that the vertex V has been introduced at the node X. Introduce edge node. Okay, so you have a node X, node, it has exactly one child Y. They have the same bags, and for some vertices belonging to pair of vertices belonging to UX, there exists an edge in the graph. Then, and we label the node X with the edge UV. Just to put a label over there, and we say that UV is introduced at X, and also there is an additional condition. We need that every edge is introduced exactly once. Should be introduced. That's an additional I should have written down over here. Otherwise, like you can keep introducing an edge infinitely, exponentially many times. Then there is something called forget node. So this has a child Y. You take one vertex and you just delete it from the bag, and that gives, it's called forget node. Then there is something called a join node. So this will have exactly two children, X, Y, Z, and their bag sizes are same. After this, what we have, we called, for every node, we define the graph Gx, where Vx is just take the union, the vertex set of this Gx, all the bags, take the union of all the bags, and edge set will be all possible edges introduced here. So if no edge is introduced here, then no edges in this subtree rooted at X. This is called Gx. So we say Gx is the subgraph of G hanging from X. Now we can assume any tree decomposition is a nice tree decomposition for the purpose of algorithm design because of this theorem. It's an exercise that if there exists a tree decomposition with at most k, then we have a nice tree decomposition with at most k. Then we can get a, and also we can find it in at most this much time, and the number of nodes will not increase too much. That's that. Width was the maximum bag size minus 1. So let's now come back to the problems which you have the T-fair vertex cover. Now we have an extra thing in the input. It's called an ICO decomposition, and the parameter has been changed to the width of the decomposition. Same for the feedback vertex set, and this notation TW is the width of the. Okay. How do you solve it? We solve it by dynamic programming algorithm. Is that what we do? This is that for every node x of that decomposition, and you have x. This has a bag called phi x. Take any subset of phi x, call it S, and you have a, remember the t tuple ki from 1 to t. Now you take all possible t tuples from the 0 0 0 0 to k1 k2 k. You take one of them, call it r1 r2 up to rt. Okay, such that each ri is in this bound, so it's like within the ki. And then what you do, you define this indicator variable or something. The table entry is that at the node x, for the subset S of the bag phi x, and for these tuples which are bounded in that lattice, we will put the entry 1 if gx, which is the subgraph hanging from the node x, has this fair vertex cover which intersects the bag at S. So if x is a node, you take the graph gx which is hanging from this node. If this graph has a r1 r2 rt fair vertex cover such that that vertex cover intersects the bag at x at exactly S, then we put 1. So any questions regarding the definition? Otherwise we put 0 in that. Is it okay? So okay. Now if all these entries have been correctly evaluated, then notice here we can say that G has a T-fair vertex cover if and only if this entry is 1, R is the root. So the graph hanging from G, the GR, that the graph hanging from the root is the whole graph. And I said the root the root node is empty. So you have just one choice for S, empty. And you just need to check if for Ri equals to, for all Ri equals to Ki, if that entry is 1. Then we have a vertex K1, K2, Kt fair vertex cover of GR which intersects the empty set at the empty set. That's the thing. So now how do you compute these entries is the thing. So let's do it. Okay. Suppose, okay, we'll do it inductively. Like so we start from the leaf nodes. Okay. Suppose X is a leaf node. What do you do? Now check for that Ri tuples where all of them are 0. Leaf node is empty bag, empty graph. So any vertex cover is of size 0. So they have no colors. None of them have any colors. I can say this because every vertex should have at least one color. So if there are no colors, that means it's an empty. Then for this entry, we put 1 because empty graph will have empty vertex cover 0 0 0 fair. Otherwise, for all other values of Ri's, we just put 0 because. Okay. Now let's do the forget vertex, how do you think this will work? Like even if, let's say, instead of Ri's you have K, Ki you have K, just forget about the colors for now. So how do you think this will, you have S here, this is a forget vertex, so how will S look here? Uh, that too, either S will look like S, or since this is a forget node, you can have S will look like S union singleton Y, V. The, yeah, forgets the vertex V. So now if either of these two cases you had one in the entry, then you should have one in the, this sign is the Boolean OR, 1 plus 1 or 1, 1 or 0. Does this make sense? Okay. Now what if we introduce a vertex? So you have the node X, node Y, you have some S. Okay. If this S, so there is one extra vertex here, just one, V. Apart from that, everything else is the same in both the bags. If this vertex does not belong to the subset S, then it's the same, we should have the same as, because this is an isolated vertex for now in GX, just one vertex. So the same value should reflect here. Now, if it is in this here, then what? And for some color, as it is in S, so to evaluate my this value, arise, I must have a vertex cover which will contain this, sorry, what do you call, vertex V. Now, if it is the case, for some color of V, I'm not allowed to pick any vertex of that color, then I must put an entry 0 here, because it is in S, I had to pick the vertex V, but the color bound says I cannot pick it because there is some color in that vertex V for which I'm not allowed to pick any vertex. So that means there is no, the conditions in the definition of this DP entry are not satisfied, so therefore we put it 0. Any questions? Okay. Now, for every other case, what do? You just delete S from V, and whatever value was here, you just put it away. So if it was 0 here, put it 0, 1 here, 1 here. Oh no, sorry, I made a mistake. These two are same sub-cases of the same case. The first case is when V is not in S.
Why will you have basically S minus V?
Yes. I made a mistake. The first case is when V is not in S. The second case is when V is in S. That will have two sub-cases. One is when you have to pick V, but you cannot pick V because the color budget doesn't allow it. Now, if the color budget allows it, then what you do? You pick it in S. You delete V from S. The thing is that the color budget should also be affected because you have deleted one vertex. So what will be that? That is, if Ri is, the ith color was of V, then Ri prime is Ri minus 1. If the ith color was not in V, then it's the same. And this is a roundabout way of writing that. I just put it to save space. Okay. The next is how we deal with introduce edge node. So what we have, the bag is the same, X and Y. Only thing that this has an extra label for some vertex per UV. This is an extra label that the edge UV is there. Okay. Now, suppose there exists, you're taking a bag, a subset of the bag S. Suppose this does not intersect the set UV, means it contains neither U nor V, then you put a 0 here, because vertex cover must have, for every edge, should pick at least uh, sorry, one vertex. And I'm saying that the vertex cover intersect this bag exactly at S, which does not pick either U or V. So therefore, is 0. You cannot have such a vertex cover. Now, otherwise, whatever was here, if U or if either one of them belongs to S, then whatever value was here, just put it here. Okay. Any questions? Okay. Now, what do we do in case of joint nodes? Now, let's recall the picture. You have X, Y, Z. All the bags are same. Okay. So you consider all tuples AI which have this bound 0 to Ri. So now this. And how do you evaluate this? You need to evaluate this one, because for the node X, for a subset of the bag phi X, and for this R1 R2, you evaluate this using this expression. Now, what is this? Okay. For now, focus on this part. I'll tell you why this is later on. Notice here. So AIs are tuples, T tuples, and each AI is bounded by Ri and 0. Okay. It's just how, if something intersects here at S, it definitely should intersect, because the bags are same, S and also S. Because if a set intersects this bag at S, it must also intersect these two at S. Same set. So, okay. Now, for some AI tuple, suppose you had call it and okay, let me just, you want a vertex cover of size K, and there exists a vertex cover of size, say, K1 here, then you must have K plus mod S, mod minus S minus K1. Yes. Yeah. Sorry, I got relations confused. So now just think about a normal vertex cover without colors, just to explain it, make it easier. So you just need a vertex cover size K for the joint node, which intersects the bag at S, and so this is the graph hanging at the node. So this node is Y, X, Y, Z, G, Y, and G, Z. Notice here, these two vertex graphs, GY and GZ, their intersection, they just intersect only at this bag. Any vertex here, which by definition of tree decomposition, any vertex from GY, call it W, which is not in this bag, will not be in GZ. Vice versa as well, because it needs to be connected. Any bags containing W must, so any vertex cover of size K which intersects any vertex cover of size K1 which intersects uh, of gy, which intersects the bag at y at s. You call it say fy. Then you take a vertex cover of size, say call it k2, which intersects the bag at node z at s, call it fz, this vertex cover. This will be a vertex cover of gx. Right? Because gx is in some sense the union of gy and gz. Anything, if you have fy a vertex cover of gy, fz a vertex cover of gz, you take the unions, it will be a vertex cover of gx. Now what will be the size of this? So k1 plus k2 minus the intersection. So k2 is, this should be k, this should be k, because I'm using my foreknowledge, so this should be k. So therefore, if k1 is fixed, then k2 is k minus k1 plus mod s. So this is what we are doing over here, but with colors restriction. So for a1, a2, a2, plus the intersection. I said k2 is what? K is the Ri here, plus the intersection minus whatever k1 was, so which is the ai. And you need to take an AND of this, Boolean AND. So both are 1, only then you get 1. Right? Now, why did I do this one? This is the same as the entry. Like what I want is that once this has been, okay, initially all entries are 0. I should have told it in the beginning. Once this has been made 1 for some AI, I don't want it to become 0 for some other next AIs. So I just make an OR over here. 1, it has become 1. So any questions? Now the running time of this algorithm is some polynomial in n times 2 to the power t, because if the tree width is some tw, then you have 2 to the power, back size is what? 2 to the power tw plus 1 back size. So you have roughly 2 to the power tw plus 1 choices. And if you note is that all these steps, they could have been done in polynomial time. So there is an FPT where the parameter is tree width. T subscript over tree width. Just
You're computing this Boolean function and then
okay.
is that
Once you have done all the things, then you go to the root node and check for this entry. If this is 1, then you have a. Okay, so this is done. Okay, now we get a FPT algorithms, a regular FPT algorithm for the vertex cover. So I will 5 minutes more, 5 minutes more. Okay, so suppose there is a vertex of degree 3 or more. I'll tell you what happens when degree is at most 2. So then what you do is, let V be a vertex of degree 3 or more. You have this, say, G and color, yeah, G the coloring function, and the this was your input script T. I don't know how to write this. Okay, whatever. This was your input. We'll now do branching. So branching essentially is you take you just do recursive calls based upon what condition has been satisfied. So you'll have two branches here. One is you take a vertex of degree 3 or more, you delete it, and whatever was affected from the colors, because if you delete one vertex, you have chosen all its color in the solution. So therefore, if the ith color, if V is a vertex you are deleting, then in G minus V, you're deleting in the sense that you have put it in the solution. So if ith color was of V, then Ki prime will be Ki minus 1. If it didn't have, then Ki prime is Ki. So with this, you call a recursive call where G minus V, C prime, and T prime is as defined here. The other is, so there are vertex cover, so there are two, there can be exactly two bunches. Either you take a vertex or you take all its neighbors. You have to, one of these must be true. So the other bunch is exactly that, except that we have to now take care of the colors. So all the elements of the name open neighborhood of V or W, which has the color I, you just delete it from Ki and reduce the parameter likewise. So you get two instances, two branching rules, and if one of them returns yes, then you return yes. Otherwise, if none of them return yes. Okay. For the base case, that is when you are in a instance where there are no more degree 3 vertices, the degree is at most 2. Notice here, this is now the graph contains only of isolated vertices, paths, and cycles. So, which means the tree width is now at most 2. So you just call the tree width algorithm, which we have already done. So that will be polynomial time because tree width is constant, and for constant parameter, FPT becomes polynomial. Okay. Now, how many recursive calls do we need? In branching, the thing is when designing FPT algorithms, you bound the number of recursive calls by a function of k, some computable function, and you show that for each recursive call, the time taken is polynomial in n. So therefore, the total time is this is FPT. This is how you can do it. Now, this is an easy exercise that if you, because we're doing 1 versus 3 branching, the recursion, the total number of recursive calls is be this much. Sorry, this will be Ki. Some 1, 4, 5. If you solve the recursion, at most summation this Ki. And in the base case is polynomial because the tree width is constant, so polynomial. A non-base case, you just pick a vertex and or its neighbor, that is also definitely polynomial. So all recursive calls takes polynomial time. So therefore, you have an FPT algorithm. And yeah, that's it. Yes, for the next day, we will discuss the feedback vertex set that requires some linear algebra and some feedback. So any questions from Zoom? Yeah. Stop share.